heard Barry speak as a moderator. Now you're going to hear him talk about research that he and Gladys Mofone, who's also in the audience, have done with respect to Fusarium. Just a bit about Barry. I don't have any good stories to tell about him or anything, but basically he's a great colleague. He's located at the mothership, University of Arizona in Tucson, and he has teaching and research responsibilities there. And I guess he had some free time on his hands, so he agreed to take on some extension responsibilities as well. So now he's got all three. And I'm glad he's younger than I am, so he can take care of all this. But I look forward to his presentation, which is entitled Detection, Management, and Impact of Soil-Borne Inoculum on Fusarium Wilt lettuce. Barry?
So today I'm going to speak about detection and management of soil-borne, or seed-borne, Fusarium Wilt of lettuce. And I'd like to at first recognize, of course, that I did not do this research. This actual research was done by Dr. Gladys Mofone, who was a graduate student in my lab several years ago. And we all know that professors stand on the figuratively stand on the shoulders of their graduate students, and we're very much indebted to them. And I'm so pleased that Gladys came to contribute to this conference and perhaps to make sure I present her research properly. Okay, so we've heard a little bit about the statistics of lettuce production in California and Arizona, and we know that it's a huge industry, with California producing the bulk of lettuce production, and Arizona coming in at 30% of lettuce production. And really, it's a single industry. It's sort of, we have production over in the coastal California during fall, summer, spring, or spring, summer, fall. Central Valley of California during fall and then spring. And then, of course, winter lettuce production is down here along Colorado River. Majority of it is in Yuma County and of Arizona, and a small percent across the river in Imperial County. But the impact of lettuce in Arizona is huge. And I hope I have these statistics correct. 50% of Yuma's county's total farm income of about 1.2 billion, yes, is due to lettuce production. So as lettuce everything that happens to lettuce in Arizona, Yuma is very interested in. And this includes disease, the incidence of disease and disease management as well. We Fusarium wilt in the U.S. first noticed in Central Valley of California in 1990, near a town of Huron. We'll come back to that in a moment. And then it was described several years later as Fusarium uxus from Lactuca. And as Tom mentioned, and Steve Quakey mentioned, it really wasn't a serious problem for a long time. Farmers, California is blessed with so much great farmland that they can simply move their crops over to areas where they haven't had the disease before. And as such, they really didn't have a problem with it. They just kept moving. Well, Arizona is not so fortunate. Arizona, we have a limited amount of ground that contributes to our world-class winter vegetable production. As such, that ground is used year after year, and it's heavily used. We don't have the options of moving away. And so it was first reported, of course, Mike mentioned this, in 2001 in some fields in Welton, and each year since then, it's progressively been reported in additional fields, more and more fields. We see it's moving around, and it's becoming an increasingly problem. We cannot move away from it here in Arizona, and the disease continues to spread. Okay, now the possible means of introduction into Arizona. We've talked about this already with several of the speakers, of course. Fusarium species are common soil-borne inhabitants, and their movement and their capability of movement in soil is well known. They're also well-known seed contaminants as well, and their transmission via seed is well known. And many of these other forma specialis or special forms of Fusarium have been known to be seed-borne and are moved via seed. And this includes on tobacco, on melons, on cotton, and on tomatoes. We know that it moves via seed, clearly moves via seed with these crops. And as I mentioned, California and Arizona really is a single industry, and it's an industry that's on the move. We start with production, let's say in the summertime in the Salinas Valley, and it moves to the Central Valley in the fall. Then it moves to the desert regions in the winter, back to the Central Valley in the spring, and then back over to the coast then for summer production. And with this movement of the industry comes the movement of machines, the tractors, the harvesters, and associated equipment. And so it's very likely that we get a movement of, unintentional movement of soil material along with this machinery. And of course, many people will say, "Oh, well, we got Fusarium wilt from the dang soil on the machinery that comes over from California." Well, we also know that seed comes from California as well. 70% of U.S. seed production, lettuce seed production, is in San Joaquin Valley. Interesting, near the town of Huron. Okay. Approximately 80% of the seed used in California and Arizona is produced in this region, with some additional imports from South America and Australia. So it is very likely that seed-borne inoculum could be contributing to this introduction as well. So, and actually, if we look at the distribution of Fusarium wilt around the world, and we can see how it was first discovered, and it's moving into these different countries on these different years, primarily race 1, of course. There's only one way it can be moving through these countries, and it could be through contaminated seed. So the purpose of our research was to focus on seed-borne inoculum. And our project was a very comprehensive project. First, we wanted to examine the phylogeny of Fusarium oxysporum, Fusarium oxysporum form species lactuca, to understand the diversity, the genetic diversity, to understand if we can actually develop methods of detection that would be comprehensive. Then we wanted to look at developing these methods for detection of Fusarium oxysporum lactuca on seed. We wanted to test lettuce seed used in Arizona. We wanted to find the smoking gun. We wanted to investigate the potential of lettuce seed to becoming contaminated. And then, of course, we wanted to determine the origin of the Arizona isolates through some population studies. And I'll be talking about most of this. I don't believe I have time. This is another talk altogether down at the bottom, population studies. So our first agenda was to look at the diversity of this pathogen, using isolates from California and Arizona. We have some Japanese isolates in here. We have other Fusarium species. And what we found out really quickly here is that all of the Forma species lactuca was closely related, whether it came from Arizona, California, Japan. It was all race 1. Okay, and we also said, and you've seen this in some other presentations, that race 2 is unrelated to race 1. It evolved independently. But what's important in this is that we have here some isolates of Fusarium oxysporum not pathogenic to lettuce that were from some of our native strains here in the Yuma area. And we can see that these pathogenic isolates are unrelated to those strains. So that suggests that it did not originate here in Arizona, that it was imported. Okay, and there's many different ways to evaluate seed, to test seed for infestation of a number of various pathogens, whether fungal or bacterial. You can do your seedling grow-out tests, freezer blotter methods. We're all familiar with these, semi-select. We can see that their specificity, sensitivity is low to moderate. They take a lot of time. But then when we move into molecular methods of detection, such as serology, conventional PCR, these magnetic capture, hybridization techniques of PCR, some of these other molecular-based methods, our time for detection is very quick, as well as the sensitivity is very high. But we also know that there's some real challenges to doing PCR detection on seed of pathogens, and these challenges are well known. Low DNA content, in contrast to populations of bacteria on seed, which might be in the thousands or perhaps millions of propagules per seed. With fungi, sometimes you might only have 1 or 2 spores attached to each seed, so you have low DNA content per seed. And then, of course, we have the presence of inhibitors with all seed assays. Phenolics, carbohydrates. So one of our first challenges was, of course, to develop a method that was sensitive and specific for this pathogen. And we had to Dr. Fung developed a nested PCR technique, which involved a sort of a double PCR, where we get first amplification to build up our templates, and then a second application to do final detect for high sensitivity. And this didn't come out right. Okay. We also had, we looked at 1,000 seeds, and what we did here is we pre-incubate these seeds for 4 days, so we're actually taking some time. But we pre-incubate the seeds to let the fungus that is currently present grow up on the seeds and actually colonize the seed further, increase fungal biomass. And then we put these seeds into our assay tubes, but we do not grind up the seeds. We do not grind them up because that's going to release all these inhibitors to PCR. We do our phenylchloroform extraction simply from the exterior of the seed. We add compounds to help absorb some of the phenolic compounds. We add a DNA binding matrix and clean up, and then our PCR. And what's important to realize here is we never, and for those who have done PCR detection we never precipitate our DNA. It's always in solution. And we found that by precipitating your DNA, sometimes you bind it to some of these inhibitors and you can't get rid of it. So we never precipitate our DNA. Okay, these are some of the results of our PCR assays, and you can see right here the effect of using a nested PCR assay. This is our first amplification. Here we're amplifying up to 200 picograms, or down to 200 picograms of DNA, and then our second PCR amplification, we're actually amplifying down to between 2 and 20 femtograms of DNA. Very, very sensitive. And of course, we want to use this in a seed assay as well, and we artificially contaminate some seed with our target pathogen at different rates of 100%, 10% infestation rate, 5%, 1%, down to 0.5%, down to 0.1%. Where's 0.1? Somewhere down in here. And we find that our method, this method for assaying seed, was very sensitive, and we can detect the pathogen in as low an infestation rate of 0.1%. That was one seed in 1,000. Okay, so we decided we were going to use this assay and look at the population, or look at the presence of Fusarium oxysporum on lettuce seed used in Arizona. And over three years, 2004 to 2006, we tested 88 seed lots, and these were seed lots provided by some of the seed producers that were not pelletized. They were before they were pelletized, with a little clay on the outside. And we used both direct plating, a very conservative method, testing 1,500 seeds per seed lot, and then using our PCR method, and we looked at over 5,000 seeds per seed lot. Interestingly enough, we didn't find seed contamination at all. Not a single bit of seed used in Arizona during that period, at least what we tested, was contaminated with the pathogen. So that made us think, well, how is this happening? The smoking gun says it's seed contamination. So what we found is that the nested PCR was very specific, and we thought that this method could also be used to modified to use for testing the presence of the pathogen in soil and in plant tissue. And many of the other researchers out here in some of their labs have also looked on even more specific primers, even more sensitive primers that could enhance this method of detection as well. But again, we found no commercial seeds infested with the pathogen. Okay, so then we wanted to say, how can this be? How does the seed become infested? And so we set up some greenhouse studies where we looked at several cultivars that were moderately susceptible, both head lettuce, leaf lettuce, and romaine type. And we had to use moderately susceptible cultivars because if we used highly susceptible cultivars, they would simply die and we would not get seed production. And we wanted these cultivars to be able to produce seed, and we were going to grow the plants to maturity, harvest the seed, infect them by both a soil drench and a root dip method. And Dr. Fujinaga already mentioned some of these methods. And then we wanted to assay for the presence of the pathogen as we went up the inflorescence and up into, finally, the seed. And here's some of taking sections of this inflorescence, looking at basal nodes, middle nodes, upper nodes. And of course, in the basal nodes, we were able to always see clear signs of infection, that vascular discoloration. We were always able to detect the pathogen. But as we moved on to the upper portion of the seeds, or the stems, they were often symptomless. And you can see here the results from this greenhouse study, our basal nodes, middle nodes, upper nodes, and our detection of the basal nodes from all these cultivars was always 100%, and down with all the way, and it starts decreasing down to finally the floral tissue, where the recovery was not high in this floral tissue. And then we looked at the seed that was finally recovered, surface disinfesting this seed, seeing if in fact it was infected or not. And we found that testing thousands of seeds here, we rarely recovered the pathogen from seed. Rarely. So it was moving up the inflorescence poorly, and then it was not colonizing the seed. But then we also find that if we mix this seed with infested debris, which commonly happens during seed production, right? At different rates, 1 to 5, 1 gram, 1 pound of, or 1 gram of seed with 5 grams of infested debris down to 400 to 1, we can find that seeds would become infested quite easily simply by mixing them with infested crop residue. Okay. The conclusion is, of course, that the movement of stem is highly restricted. It's not commonly internally seedborne, and that it's easily externally contaminated. Okay, so management of soil-borne seed, seedborne Fusarium Wilt. Continue surveys on the level of seed infestation and definitively determine, can it become internally seedborne? If it can, this is important in terms of developing appropriate seed treatments to remove this infestation. This is very important. We need to develop thresholds for seedborne inoculum that are appropriate for many different ranges of environmental conditions and growing and in different countries. We have to review the regulatory implications of this as well. And finally, we need to manage seedborne production, whether it's in California or other areas, to minimize contamination or infestation of seed under diverse production environments. And I'd like to acknowledge, of course, Mike Mathron and Tom Gordon. They've always been involved in Fusarium Wilt research here in Arizona and California, and of course some of our funding sponsors. Thank you very much.
Questions?
So the question is, what is the time when they start producing seed in Huron and when it is harvested? Gosh, I'm not sure if I can answer that correctly. I'm thinking that it must be three months for you to actually get seed production, 2 to 3 months. I don't know those specifics. Yes? So the question is how feasible it is to use real-time PCR in the detection method, and will we be able to use it to detect multiple pathogens? And yes, that's true. We will be able to use it to detect multiple pathogens in a single assay. And in regards to race 1, 2, and 3, that would be highly desirable to have such a method. And also to help us get an idea on the level of infestation we're talking about. Is it feasible to do that? Well, I think that's dependent upon the will of the industry, and perhaps, as I mentioned in that last slide, what are the thresholds? What are we really working with? And how important is that to control that level of infestation, particularly for moving it into new production areas? That's so critical. That is so critical.